Hi kids, welcome to partial fractions. I mean, look at these words down here. Students will be able to decompose fractions into partial fractions. What the heck? Decompose. I need you to think about what you did in elementary school. In elementary school, you learned how to compose two fractions or more into whole fractions. So we learned how to take, for instance, 1/2 and add it to, for instance, 2/5 and take two parts and turn it into one whole fraction. We had to find a common denominator. Then you had to change legally the numerators. And your numerator became 5 plus 4, so you had 9/10. 1/2 plus 2/5 was equal to 9/10. You composed two parts that were added together into a whole fraction. That's composing. You need to decompose, which just means go backwards. Darn it. Right? We had 1/2 plus 2/5 is equal to 9/10. You composed the sum of two fractions into a whole. Now what we're going to learn is how to go backwards. Take one fraction that's all mushed together and rip it back apart into a sum of its parts. That's what partial fraction decomposition is. We're just going to learn how to do it in the abstract, right? Instead of 1/2 and 2/5, you've got rational expressions. So firstly, reviewing that when you have a rational expression, it can be expressed as a sum of its linear factors and any irreducible quadratics, right? So notice that, which is objectives we did with division, I can factor an x squared out of here and get an x squared plus 1. Notice that I am breaking it into, I can decompose this fraction into 1, 2, 3 parts. I have an irreducible quadratic, x squared plus 1, and then another factor squared. So for example, what if you actually had 3/4 squared times 7, right? That would have come from a denominator of 4, a denominator of 4 squared, and a denominator of 7. And that's how you would have gotten the least common denominator. How many times did the factor 4 show up? How many factors did the factor 7 show up, right? And then you need to figure out what these numerators are to combine to 3. If I had given you this problem in a prior course, right, and said simplify, that's easy, simplify, right? You would have been able to get here. It is a little bit harder to go backwards and rip it apart. Rip, that's what you're doing with fractions. You're taking a whole fraction, right, and you are ripping it into its parts, sometimes into 2 parts, sometimes into 3 parts, sometimes more than that. And you just hope not. Rip. So, some notes. You hope you don't have to do the first step. If you have a rational expression and the degree in the numerator is higher than the degree of the denominator, you've got to divide to make it not so. Then you need to factor the denominator over the reals. We are not in the set of non-real numbers anymore. And then for each linear factor, if it is repeated once, then you only need to repeat it once with an arbitrary constant on the top. If this linear factor is repeated twice, then you need to make a sum of the factor squared and then the factor to the first. Again, that's like having 1/5 plus 2 over 25, right? The common denominator is 5 squared, right? But it came from 5 squared and 5 to the first. If you have an irreducible quadratic, though, your arbitrary constants involve a linear term. Okay, that looks all devastating. So take a picture of that, but you should write it down. Now, if you didn't get it all right now, that's okay, because I will take a snapshot of this and keep it on the next slide. When you do a partial fraction decomposition, the partial fraction decomposition is a sum of all of those parts. Then we have to find what those constants are to make the equation true, to make the one fraction on the left, the whole one, equal the sum of its parts. That's the hard part. So here's what I'm saying. Here's a snapshot of those notes that you were taking. So if you still need to write a little bit of it down. Now, I must admit, I don't like the whole subscript thing. I tend to just use the alphabet. I'll say A, B, and C, or I'll say AX plus B and then CX plus D. I don't really like to use all the subscripts. I get kind of lost in that. Notice here, your directions are just to write the decomposition form. You do not have to find the constants, right? So make sure to read your directions. This whole fraction on the left is equal to RIP X. X is repeated. X is repeated. Plus X plus 3 is a linear factor that is not repeated. Plus X squared plus 1 is an irreducible quadratic. So I need to include a linear term on the top. How come? Because when I get a common denominator and multiply, right, and figure out what to do with A, B, C, D, E, X plus F, I get a numerator of 5X plus 1. That's how come. So look at this one. RIP. X squared minus 4 is not an irreducible quadratic. It reduces into two non-repeating linear factors. X squared plus 3 is an irreducible quadratic, and it is repeated twice. Constant, next constant, irreducible quadratic has to have a linear numerator. Okay. Solving for the constants is a bit of a show. We're going to start with the easiest kind. We are not going to start with these two. These two would be very challenging. So let's start with this one. 5x plus 1 over an algebra 1 quadratic. Take a moment and cry that you have to do partial fraction decomposition and then get to work. Step 1, rip it apart. But to rip it apart, you've got to factor that denominator. Factor the denominator to see how many fractions you need to rip into. Rip. Right? Non-repeating linear factors means I've got two unknown numerators that when I go backwards, right? When I combine these two, A and B need to combine to 5x plus 1. Non-repeating linear factors are the easiest kind. If I have to do partial composition, I like to do non-repeating linear factors. So I'm going to multiply both sides by the common denominator, terminate the fractions, and now here's where things are going to get a little crazy. You're going to think you're going to be like, I don't know, Ms. Getz, I don't know if I buy what you're selling here. But an English mathematician called Oliver Heaviside, somewhere in the early 1800s, I think, came up with this method. I don't have to use this method, right? I can solve equations, right, with multiple unknowns. I took Algebra 1 and I took Algebra 2. I know how to solve systems of equations. But if I can make my algebra work a little easier, I can thank Oliver Heaviside. And Oliver Heaviside teaches me how to heave aside one of these unknowns. When you look at this equation, there's 3 unknowns, 1 equation and 3 unknowns. I have x, a, and b. Now, really important here is that you buy the equal sign. You do need to believe in this equal sign. What's on the left is equal to what's on the right. They are equal. They are the same. And I know I have an x, so if I choose x to be 7 and I put x in for 7 here, as long as I put 7 here and 7 here, the 2 sides will balance. They will be equal. So if I can choose any real number, now don't look at the fraction part. I've terminated the fractions, right? A shortcut that Oliver Heaviside came up with is also called the annihilation method. Bam! Now, when I think annihilation method, I think of the Terminator, Arnold. So Arnold's going to come knocking at our door here, and of all the numbers in all the world, Arnold wants to choose x to be -3. Do you see why? If you let x be -3, you're going to let x be -3 everywhere. Here, here, and here. What happens over there? Thanks, Arnold. Bye! I no longer have an a to worry about, and I just have b times what? Therefore, b is equal to 2. Thank you, Arnold. Well, I solved for 1 unknown. Guess what I'm going to do now? I'm going to let x be equal to 4 because of all the numbers in all the world. Why did I choose 4? Do you see? I went back to the original equation, chose x to be a different x, a very particular one, bye. And then x is 4 here, x is 4 here. Thanks, Arnold. Because notice what I've done. I have successfully decomposed this fraction into a sum of its parts. And if you don't believe me, then check it. Check your work. To check your work, what are you going to do? You're going to get a common denominator, which is x minus 4 times x plus 3. And then you're going to multiply this one, this numerator, by x plus 3, and this numerator by x minus 4. And then you're going to combine the numerators on top of x minus 3 times x minus 4 times x plus 3. And you're going to get 3x plus 9 plus 2x minus 8. And guess what you get, OMG? Hello! 5x plus 1. Okay? So let's do another one like that before we get nastier. Maybe pause the video and see if you can do this one without me. Factor. Rip. Non-repeating linear factors are my easiest type. Multiply through by the common denominator. Bring Arnold in. Of all the x's in all the world, I think I will let x be -3. Who does that terminate? Bye-bye. Repeat. Bring Arnold, bring the terminator in. Put 5 here, put 5 here, and use Arnold to bye-bye. Terminate the B. You have taken one fraction and decomposed it into a sum of its separate parts. Ta-da! Woohoo! Congratulations! Yay! Again, this case was the non-repeating linear factors. That's once you get used to partial fraction decomposition, when you have non-repeating linear factors, that's your easiest type. So what happens when I don't? Dagger. Step 1, factor. Ooh, that's not an irreducible quadratic. So when I rip this into parts, the first part is x, it's to the first and it is not repeating, plus x minus 2 to the first, plus x minus 2 squared. Now I don't have each one of the factors, right, themselves are linear, so I just have a, b, and c this time. So I'm going to multiply through by the common denominator, which means a has who with it? Remember, what you're multiplying by is the common denominator, which is this. So a, the x is going to cancel out, but it's going to be left with x minus 2 squared. The b is going to be left with the x and one of the x minus 2's. And the c is going to be left with just the x, because both x minus 2, the x minus 2 squared will cancel out. Now I am going to start off with Arnold. Arnold is going to get me far, just not going to get all the way to the end. What are you going to have Arnold let x be? Yeah, 2. Who gets terminated? Oh, thanks. Bye. So c times 2 is equal to what? Put 2 into here. Negative 2 squared is negative 4. Plus 4, that's 0. Plus 4. So what does c equal to? Check. Now what can I let x be equal to? Yeah, 0. Right? So negative, go ahead and let's plug in 0. 0 squared plus 2 times 0 plus 4 is equal to, put a 0 in here, negative 2 squared, a times 4. And then who gets terminated this time? You put 0 into here, put 0 into here, by. So what does a equal to? Yay. Psi. How am I going to find that b, gosh darn it? right? Do you see why there's no more Arnold, right? I don't have any more x's that I've used the two x's that will create 0, right? I have that repeating factor, and I still have another coefficient to solve for. Sigh. All right, so I'm going to erase all of this. Now remember, I did find my A. I don't know my B, but I did find my C. Right? So remember, I had A times x minus 2 squared plus bx times x minus 2 plus cx, right? But remember, we found A and we found C. So this is equal to 1, A is equal to 1, and C is equal to 2. Now, I have one equation and two unknowns. Believe in the equal sign. I need you to see what's on the left is an x squared term with a negative 1 in front of it, an x to the first term with a positive 2 in front of it, and then a constant positive 4. That has to be equal to this side. So let's expand this side. And let's clean it up a little bit. Here's an x squared term, and there's an x squared term. Here's a negative 4x, and there's a positive 2x. So that's negative 2x, right? And then here's another x thing. And then I just have the plus 4. Now remember what that's equal to. Oh, hey, you know what else I'm going to do? Factor by grouping. See what's going on there? Now I want to factor an x out of there, a positive x. And what's left when I factor a positive x? And then plus 4. Now let me do some more color coding. What if I make this x squared purple and I make this x purple? And again, I'm going to bring down what I have here. Negative 1 is the coefficient on x squared. Positive 2 is the coefficient on x, and my constant is plus 4, and these two things on the left and the right are the same. Do you see plus 4 on both sides? Do you agree that the plus 4 is the same as this plus 4? Right? They are equal. But look, here's your x term. Here's your x. What's the coefficient in front of x? Positive 2. So what must be true about this? This coefficient on x, if you believe in the equal sign, this coefficient in front of this x has to be 2. Look at your x squared. What's the coefficient on x squared on the right? 1 plus b. That coefficient, if you believe in the equal sign, must be equal to the coefficient on x squared on the left side. So what does that say? -1 is equal to 1 plus b. At the same time, +2 is equal to -2 minus 2b. I don't care which equation you solve. B is going to be the same thing. Or else you won't have equality. Check. So my partial fraction decomposition is 1 over x plus -2, and yes, you could write that as -2 over x minus 2, and a +2 over x minus 2 quantity squared. If you don't believe me, check the work by pretending I gave you this problem and asked you to combine it or simplify into one fraction. Go this way and check your work. All right, so what we did in this video was learn what a partial fraction decomposition was. We broke apart some fractions without solving for the constants, practicing breaking up both repeated factors and irreducible quadratic factors and what those numerators would look like in the abstract. And then we did 3 examples of actually finding the partial fraction decomposition, which means going all the way to find the constants. And we used the method, the annihilation method, which would come up by a mathematician called Oliver Heaviside. I like to refer to it as the Arnold method, right? Because it helps me heaviside or terminate one variable so that I can, or one of the coefficients while I solve for the other one. I still used Arnold in the last example, but I had repeated linear factors. Repeating linear factors does make my math a little bit worse because I can only use Arnold I can't use Arnold for the repeating part. But I showed you how to use equality to set coefficients equal to one another. All right, so that is the end of the first partial fraction video. The next one will continue on with more of these, of the more complicated partial fraction decomposition. I will see you then. Can't wait.